Okay. Hello, everyone. This is Russ White. Let's see. You probably know me from other things that I've done. Today, I'm going to be talking about new directions in cloud plumbing. So I'm going to start this. Well, actually, I'll just move down. And I'm going to switch to the screen where you can ask questions every now and again, so that if you want to ask me a question, you can type it into the panel there, and I will see that question and do what's going on. So this is kind of my agenda. This is my agenda. So we're going to start by talking about a review of some data center design concepts, mostly around the concept of spine and leaf fabrics and why people use them and what they're there for. And then we're going to talk about the disaggregation earthquake, what's going on right now in the world of disaggregation and why people are going this direction, and the kind of changes that that is making in the networking world. And then I want to talk a little bit about changes in the control plane. And then I'm just going to talk a little bit about future directions, some interesting things that I see out there that might be interesting for people who are in the data center space or the network operation space, that might help you understand what's going on in the future, or just things to look for, basically. So first of all, let's start with, because I understand this audience is not necessarily technical all the time, so I just want to do a review a little bit about spine and leaf topologies. So many people use spine and leaf, leaf and spine, or CLO topology interchangeably. They really, CLO or CLOS are not exactly the same thing as a spine and leaf. A CLO or a CLOS is actually what's shown on the screen here is a CLO or a CLOS. I usually call it a CLOS, but some people call it a CLO. Is really a subset or a form of a spine and leaf fabric. So spine and leaf is actually a superset of a CLOS fabric. So there are many different kinds of spine and leaf fabrics other than a CLOS fabric. So these are originally designed for unidirectional traffic flow. So what's interesting about that is a lot of people don't realize that a CLOS fabric was designed so that you would send traffic up through the fabric in one direction only, and it would be unidirectional through the fabric, so you might pick whatever link in any particular direction, but there's only traffic running in one direction. And this was originally designed to build very large fabrics out of really small, uniform switching elements, or different kinds of switching elements, different kinds of designs that were designed to be just very simple. So the original CLOS fabric was designed for a 4-port switch, so there were 2 ports on either side of it, and it was a very small fabric. But the idea is that you can build very large fabrics out of really small switches like this. So you might note the numbering that I'm using here, that I have A and 1 and B and 2, and then I have this T0, T2, T1, T0 thing here. This just helps you to understand what device I'm talking about, router or switch, in this topology as I'm going through. A lot of different numbering schemes are used for this. This is just a simple way for me to get around it and understand things. So T0 down here would be connected to host, and T0 down here would be connected to host, and then these would be considered your spine switches, and these are considered your super spine switches here at T2. So this is basically how I number things, just to make it easier to understand where we're talking about in the fabric at a particular time. So again, CLO fabrics or CLOS fabrics are designed originally, or spine and leaf in general, were designed for circuit switch networks, which means that if a call is coming through the network, starting up here at A1, that you would actually set up a circuit that runs through the network to some device sitting down here, say at C5. So at this T0, you would have a phone or some type of device attached, and what you would do is you would set up a circuit, and that circuit would actually be edge to edge in the network. In a circuit switch network, of course, the calls or circuit requests are accepted on a capacity basis. So if I'm at A and I have a bunch of devices connected, and I use all 4 of my outbound links for different calls, I would say I can't accept any more calls. This is one reason why I look at a fabric like this, what's called a fabric like this, and I can say that it's non-blocking, because it doesn't block in the fabric. I won't drop a circuit connection in the fabric itself. I'll only drop circuit connections at the edge of the fabric, never in the fabric. Another interesting thing to note is that you have exactly the same number of connections out of every node as you do in every node. So it is possible, if you are sitting here at, say, D5, that I only have 4 inbound connections, that in theory it's possible for A to originate 4 calls towards D5, and then B to come in and try to originate a new call towards D5 or a new circuit connection. This would actually block. But again, it doesn't block in the fabric, so the fabric itself is considered non-blocking. So if traffic only passes over one direction on this fabric, then really I don't have a lot of a need for a control plane. I can do this thing where I say at A host sends a packet, or I start a circuit switch, and then I come down here and I say, well, where should I go? Should I go to 2A, 2B, 2C, or 2D? Well, as long as I know where the destination is on the other side of the fabric, I actually don't need much of a control plane. I can actually use like bridge learning or something like this. I just send the traffic towards a next closer device across the fabric, and that's going to give me what I'm going to do. In packet switch networks, however, I don't send traffic unidirectionally. Again, the CLO fabric or the CLOS fabric was originally designed for a simple unidirectional traffic pattern across the fabric. In packet switch networks, of course, I don't do this. I actually have bidirectional traffic on each link. Because I have bidirectional traffic on each link, I have created what is called a folded CLOS, or a folded CLO in more familiar terms. So to fold a CLOS just means that I'm making the links bidirectional, that I'm going to route traffic in both directions. When I fold a CLOS or a CLO in this way, it is important for me to realize that now I must have a much more complex control plane sitting on top of this spine and leaf fabric. I can't just use this very, very simple push it to the next hop kind of control plane and very basic discovery about where things are going to be. So what happens is that instead of having very simple switches here, I need a more complex switch, or even a router that can do equal cost multipath sharing across multiple links. It can do topology discovery. It can do destination discovery. It can find things in different places on the fabric. So now I need a more robust control plane. This type of folded CLOS or folded CLO is what I actually use in most data centers. Well, really not a folded CLOS. I actually use a butterfly, but it's a form of spine and leaf fabric. So before we go much farther in trying to understand what this is, what do I mean when I say this is a fabric? There's a lot of confusion around this term. People use fabric for all sorts of things like wide area networks and campus networks and stuff like this, and that's not really what a fabric means. A fabric is a very specific set of mathematical properties. It's a topology with a very specific set of mathematical topologies. So the specific qualities that we talk about when we deal with a fabric are, first of all, each part of the fabric repeats throughout. You can see that I've circled the red part here, and it's identical to the red part over here. So that's what it means. These topologies are repeatable. I can actually take any section of the topology and repeat it any place else in the topology. So the same is true of these two blue squares. These are both repeatable. I'm going to pop over here real fast, and no questions at this point, so we'll just keep going. I just want to check every now and again to make sure that nobody's asking questions over there in that web browser. So this means that each part of this is repeatable in this way, which means that it's called a regular network topology. That's the terminology used for this. It's a regular network topology. Another interesting thing about a fabric, or what makes a topology a fabric, is that it scales out rather than scaling up. So what I mean by this, well, we'll get more into definitional about this in just a minute, but instead of creating or adding, if I have a network and I have 10 devices connected or whatever it is, and I do this, and I want to increase the number of devices, I can make this device bigger in the middle. I can keep adding slots to it, or I can keep adding things to it. And this makes it a scale up. I'm scaling up a single device to make the network bigger. In a cloth fabric or a cloth fabric, what I can do is I can keep adding sets of devices out here on the edges and connecting them in like this. And as long as I continue to add these devices and I cross-connect them all the way across to everything exactly like the existing fabric is, I maintain all the same characteristics as a fabric. So this is what makes it a fabric, these things right here. It's regular, which means the parts are repeatable, and it scales out rather than simply scaling up. Another interesting attribute here is that you can actually tune for oversubscription. So we'll talk a little bit about what oversubscription means in just a minute, just again to give you this background of what is going on in the data center fabric world, just so that you can have background around disaggregation and the changes in control planes and stuff like that. So let's talk about this a little bit more, about this concept of non-blocking and non-contending. In a non-blocking fabric, no traffic is ever dropped on the fabric itself. This is really only possible in some configurations of a non-folded clo fabric, or a specifically a clo fabric. There are some binaries and other types of fabrics that are also non-blocking, but by and large, it has to be a non-folded unidirectional fabric that is going to allow you to non-block. And again, if 1A, 1B, 1C, and 1D all set up circuits destined to 5D down here, you're going to have different paths you can take through the network to get to that destination without overflowing the amount of bandwidth available at D5 to accept all of that traffic. This is really not easy to do in a packet switch network because I have traffic going everywhere in both directions all the time. So in a non-contending fabric, which is what we would call this, a non-contending fabric, traffic can actually be dropped. So it just means that I can normally find, non-contending just means that I normally do not end up in queuing situations so long as I have built the fabric correctly for the amount of traffic I intend to carry, and that I am doing ECMP, I'm doing equal cost multipath and other things to make sure the traffic is spread across the fabric as best as possible. So I'll define that real fast. ECMP just means that at A, when traffic comes in, it is going to load share across all four of these available paths. So if that load sharing is unbalanced in some way, it means that I'm going to end up with contention as I build up more and more traffic on the fabric. So I've got to build the fabric in a way that allows me not to have contention to make it non-contending. So if a hotspot develops or something like this, there's different situations where you can get into. Then you end up with a contending fabric. So let's talk about the concept of oversubscription real fast, just so that, again, we get all the background in here to understand kind of what's going on in the data center world. Assume all of these links are at the same speed. So each one of these are, say, 10 gig links or 100 gig links or whatever they might happen to be. If A and B both fill their links towards C, therefore they're sending 10 gig of traffic. There's only 10 gig of available bandwidth on this C to D link. So that means that link is going to have to drop traffic. C is going to have to drop traffic to get the traffic onto the link or get the traffic to D, because there's just not enough bandwidth available. So since you can have 20 gig in this situation feeding into C, and you only have 10 gig sitting here between C and D, this is called a 2-to-1 oversubscription. So this is oversubscribed by 2 to 1. So this gives you a sense of what oversubscription means. I can, of course, increase my link speeds. If I made this 10 gig and this 10 gig and this 100 gig, there would be no oversubscription here. In fact, it would be undersubscribed on this C to D link. But if I were to make them, again, let's say I make these 10 gig and these 10 gig, and this is 15 gig, then I would have a 1.5 to 1 oversubscription rate, because I have 1.5 to 1. I have 20 gig to 15 gig that I can send. you can actually, using these types of formulas, figure out exactly what your oversubscription rate is. All you do is you take all of the values of all the edge ports, you add all those together, then you calculate it over the speed of the internal links in the fabric. This will give you your actual oversubscription rate. And of course, you can scale it up. You can increase the link speed here and give yourself more bandwidth, which will reduce your oversubscription. The other thing you can do is add more links or even add more devices, which is essentially what you're doing in a class fabric, is adding more devices with their attendant links. This allows you to double your link speed here. So if everything again was 10, I would actually be not oversubscribed at this point because I have exactly 40 gig of points in, 40 gig in, and so I should have only 20 gig in and 20 gig out. So this is how you can do it. You can add links and scale out, as well as increasing links to make it scale up. All right, so why do we use spine and leaf topologies? Why is this such a common topology in large-scale data centers and hyperscalers and stuff like this? The primary reason is that the spine and leaf topology is what we might call a universal topology. So if I take all sorts of different topologies and I think about all the topologies I can build in a network, I can build things like rings, right? I can build a ring network where everything is connected. I can build a hub and spoke where I have a spokes connected to a hub. I can build something like a full mesh. Each of these has different kinds of characteristics for an application running on top of them. If I look at each one of these and I think about what are my jitter and delay requirements, how does the traffic flow work between these things, and I think about what kind of application I might put on top of these, I can see that each of these might fit a particular application well. But what happens if I end up with a bunch of applications that want to use different kinds of topologies for optimal use? What I really want in this situation is I want what's called a universal topology. A universal topology just means that I can take any topology, I can emulate any topology on top of this universal topology with a minimal amount of loss of efficiency. So if I take a ring and I impose it onto a spine and leaf, by doing an overlay, by doing tunnels or something like this, the ring topology will have some amount of loss of efficiency when you're implementing it on top of a spine and leaf, but it won't be very much. The same thing with a full mesh, and the same thing with a hub and spoke. So there's actually been research done to show that a spine and leaf topology, in particular a class fat tree, what's called a fat tree, a class topology that's built as a fat tree, will give you the best emulation of every possible topology. So this essentially means that no matter what application you throw at a class fabric or a spine and leaf fabric of various types, you will get the best possible application performance with the least amount of degradation in what you're doing. So the most commonly used topology that we see in hyperscalers is really a spine and leaf. It's not a class, but it's called a butterfly, or perhaps some people might call it a benes. It's a form of a benes as well. And benes is named just like Claas is. Claas is named after Charles Claas, the guy who worked at Bell Labs who invented this. Benes is named after a guy named Benes, and it's essentially just another form. Here you have your host or your servers attached to your edge devices. These are what's called your top of rack switches or your T0s. In some environments, you might call this a T7 or something like that. Just things might be reversed. And then you have these four, what are called fabrics, in this, or three in this case. Most people build them with four, but I've only shown them with three here, in the middle. And then each one of these top of racks connects to each of those fabrics. So each of these fabrics inside is a three-stage class. So what you end up with is a five-stage spine and leaf, or a five-airy spine and leaf. So this is typically what you see. This is what you see at Microsoft, LinkedIn, Google, Facebook, you name any of them, eBay, Adobe, Disney, anybody who runs a large hyperscale or a large-scale database or a large-scale data center fabric will typically run this kind of a fabric. So now let's talk about what is going on in this world. If I look at that type of fabric, how it's traditionally been built is with chassis boxes and highly vertically integrated devices from vendors. So now let's look at what's going on in this world, and think about what I'm seeing happen as far as trends. We live in very, very interesting times as far as data center fabrics go. There's a big wrecking ball coming across what we normally associate with things, and it's blowing out all this stuff all over the place. So what is that wrecking ball? There's a lot of different things. There's software-defined, which everybody's probably heard of, software-defined networking and what's going on there, or kind of at least has heard of it, may not know what's going on there, but has at least heard of it. There is white box. What is going on with white box and the concept of replacing my vendor gear with a generic box that I call a white box. In reality, white box, in my opinion, is a little bit overblown. Most people are doing white box, or they're using vendors and they're disaggregating with vendor gear in some way. But nonetheless, white box is a major movement and things are going on in that space. Open source. There's been a lot of open source and quasi-open source. Companies like Cumulus selling a network operating system that you can run on anybody's box, or not anybody's box, but a larger set of hardware vendors. And then you have other open source movements going on where people are looking at not just open source, but again, like a bright source, like I'm buying the software from one person, I'm buying the hardware from someone else. So where we see happening here is we actually see these things crashing into what I would consider our dominant players, which may be Alcatel, maybe Cisco, might be Juniper, might be, I don't know, all these various people. And it's blowing out this idea where people are piecing things together from a lot of different companies all at once. They're going software defined, they're going white box, they're going open source, but they're also buying stuff from particular vendors. Like people still buy Cisco boxes, but they run their own control plane on it. People still buy Juniper boxes, but they run software defined on top of that. People are buying Barefoot switches and running their own software on top of that. They're buying Cumulus software to run with various kinds of hardware. There's another entire move in this space around doing glass fiber, doing glass-based switching rather than, or optical switching rather than IP switching, packet-based switching, which is things like Fiber Mountain, companies like this. So it's very interesting because a lot of stuff is going on in this world right now. My prediction is there will not be one data center market in the near term, but rather a broad spectrum of markets. We're still going to, what we've almost done is we've almost standardized on this spine and leaf cloth type or beignets or butterfly style fabric, but we're building these fabrics with a lot of different things instead of one thing. So this, my basic concept here is that there won't be one data center market. There's going to be a lot of different data center markets. There's going to be highly integrated data center markets where people are buying from companies like Apstra and Ava, Avi, and people like this, and are actually thinking about how they build things out of multi-vendor gear. And at the base level, there will be people like hyperscalers like Microsoft and LinkedIn and Google. They will be building their own software. So it's going to be all over the place for a little bit. Why would you disaggregate? Why is disaggregation taking hold? Why are we getting into this market? Because it seems so much simpler just to buy from a single vendor. Why am I actually buying from all sorts of different vendors or building things myself? The first reason is that my software architecture is tied to my business processes and my application architecture. These are really important. I want to bring my software life cycles and my software architecture closer to my business rather than closer to my vendor's business or rather than closer to my hardware. So to do this, I need to separate my software from my hardware. Hardware architecture is also tied to technology development and vendor product cycles. And I don't mean Cisco and Juniper and Arista and things like that necessarily. I mean people like Broadcom and Barefoot. Going all the way down to the chip level, I'm actually seeing a very rapid change in my hardware capabilities, and it's just rolling very fast. So in order to want to take my software architecture and split it off of my hardware architecture so I can change my hardware whenever I want to. The appliance model that we're all accustomed to tends to tie these two things together. I buy a piece of hardware, I put it in my data center, and it is tied software to hardware all together in one thing. So what I do in disaggregation is I actually separate each of these things. I separate my management, I separate my control plane, I separate my network operating system, the wrapped sheet metal, the chips and boards, all of these things, I separate them out, and I can choose a different vendor or a different source for each one. I can actually choose what I want to own and what I don't want to own. If I'm a smaller company and I don't want to own any of this, I can buy these pieces up here from one company and these pieces down here from a different company, let's say. Or I can buy all of these from the same company, but I buy them as separate pieces or separate line items, separate SKUs on my contract. It's really up to me how I'm going to do this. So if I'm a larger company, I might build this myself. I might build these two myself. I might build this as a separate unit or buy it from a separate company. And I might buy these two as a separate thing. It just depends on what I want to do with how I want to buy things. This unties my business model and my requirements from the vendor's product cycle. So in other words, I'm building my network for my business, not for all of the vendors' customers out there. So again, Elements, Whitebox, and BrightBox, commercial and operating open source network operating systems, commercial and open source control planes. So let's look at some of these things. In the hardware space, of course, I have a number of chip vendors. I have Broadcom, Barefoot, Cavium, Mellanox. Cisco and Juniper are not giving up on building their own hardware, their own silicon. These people are often wrapped sheet metal by Delta, Alpha, QCT, Acton, Solistica. Cisco, of course, is sheet metal wrapping Barefoot and Broadcom and their own stuff. And Juniper does exactly the same thing. They do their own stuff. They also do Barefoot and they do Broadcom. Dell primarily sheet metal wraps Broadcom and Barefoot, but they do some Cavium and other things as well. So essentially, you can go pick the chipset and you can buy the sheet metal around it. This is very much like buying a laptop. I can buy an AMD processor. I can buy an Intel processor. Or if I'm buying servers for my data center, I can buy ARM or I can buy whatever I want to for each particular server brand. So software, there is a ton of software out there. So let's looking at something like network operating systems. There's 6Wind, IP Infusion, Cumulus Cells, works with open source Linux based operating systems. Of course, Juniper, you can still buy there. Junos, LabN does a lot of consulting and types of things around their doing modifications to Linux-based network operating systems. Sonic is an open source. VMware does, of course, some virtualized stuff. Cisco has Cisco IOS, NX, and XR. Dell has its own operating system. Big Switch has an operating system. Arcus is a new one that just came on the market that does their own operating system. RT Brick has one as well. So there are also routing stacks. So on top of your network operating system, so you have your hardware, you have a network operating system, then you need a control plane. So the control planes are lots of different things. There are open source ones like GoBGP, there's Bird, there are a bunch of commercial ones, IP Infusion. Cisco, of course, has their own routing stack. Juniper does. Arcus, again, has their own routing stack that is newish. So there are all these different ones. There's actually FR routing, which is probably the most widely deployed OpenStack. In fact, I would guess it is the most widely deployed OpenStack routing stack out there. This is a collaboration of a lot of different companies, including LabN, 128, NetDef. You can see all the names on the slide. Cumulus, Big Switch, Orange, ISC, Open Source Routing, which is all these different places. And FR routing is actually a part of the Linux Foundation networking project set. So there are all these people, ATC, that are using this. And there are other people who are using this and shipping this as commercial product as well, or part of their commercial product as well. So there are a lot of different people that are using FR routing. It's a huge project, and it's probably the best known of the open source routing stacks. So another point that you can get into with disaggregation is externalizing your fabric. Now, normally, if I'm building a data center, what I'm going to do is I'm going to buy a vendor box, and it's going to have essentially a small or a cloth fabric or a cloth fabric inside of it, a three-stage cloth fabric. And that three-stage cloth fabric is going to tie together all the line cards. So I'm going to build a chassis. I'm going to buy a chassis, and it's going to have a cloth fabric, and basically that cloth fabric is this big red square in the middle. So what a lot of people are starting to do is they are actually eliminating that chassis. And by eliminating that chassis, what they're doing is they're actually disaggregating, or they're externalizing the fabric. So they're actually they're building this internal cloth fabric that you would normally buy as part of a chassis internally instead. So why wouldn't you want to do this? Why would you want to have a non-chassis type of thing? There's a lot of reasons. Number one, it's too complex for some companies. Some companies consider, now this is again, not everyone is doing this. Some people still use chassis. They use a mix of chassis and disaggregated fabrics. But the reasoning behind the people who are getting rid of chassis are things like they consider the chassis too complex. They don't understand the backbone that the vendor has built. So they want to understand better how their network actually works. So they are looking at getting rid of the chassis so it's externalized. They actually own all the 1RU boxes, and every switch port has a processor sitting on top of it. Some of these people consider the chassis too difficult to troubleshoot. Just because there's internal backplanes, there's internal back pressure, there's special commands. Essentially, once you get inside the chassis, you have to call the vendor to troubleshoot it. And some of these people just don't want to do that. They actually want to manage their own troubleshooting, even at the chassis level. They consider it to scale up. Like, instead of building more bandwidth, you actually just build a larger box or buy a larger box. Too much black magic. Fixed format is too difficult to drive density and too much sheet metal. So the other option you have here is you buy 1RU boxes with 48 or however many ports on the front, and then you just stack them up. This is a fixed format 1RU process, and this is what most people are doing. The problem with the fixed format that you run into is I have sheet metal and power supply around every one of my devices that's being used to build my cloth fabric. So every circle or everything in this fabric is a separate 1RU box. So that includes sheet metal, that includes power supply, that includes cooling, that includes everything. Everything is a 1RU box. When you get 1,000 or 2,000 of these 1RU boxes in here, you start thinking, I'm going to do that, and then I'm going to have 1RU servers. So now I have all this 1RU stuff, and I'm actually doing a lot of cabling. So what people are starting to do now is look at these types of standards like Open19, where you can stack a lot of stuff into a single chassis. So now I take these brick cages, I put all of this stuff in here, and I actually have shared power and shared uplink and things like this that I can do to reduce the cabling and make everything more uniform. So the Open19 is one of these. Google is doing OCP, Microsoft, other people are doing OpenRack, part of the Open Compute project. So that's another one that's very similar. This is a 21-inch rack. This is a 19-inch rack. That's one of the differences. Facebook, this is a picture of Facebook's old backpack system, which was essentially the same sort of thing. And Facebook has moved beyond this and gone into version 2 and other things like that. So the move is on. Another thing that's going on is the cabling and hardware side. The move is on to 100 gig optical. So most large-scale data centers now are operating in with a single QSFP or a single optical interface and optics in the entire fabric. So what they're doing is they're actually running a 1RU box or on one of these card cages, a single slide-in chassis type thing. And they'll run just 8 or 16 QSFPs that are plug-in modules that run out to a single cable. And then they'll run an octopus cable that actually breaks that out into multiple 10 and 25 gig links. And then these will actually connect to the servers. So this allows you to run a single SKU for all of these optical interfaces everywhere in the data center. So you can run 10 gig down to your server, and then you can run 100 gig up to the next layer in the cloth fabric or in the butterfly fabric, whatever you're using for your spine and leaf. So this allows you to reduce the number of SKUs that you have, the number of physical devices that you're keeping on hand, and allows you to develop tools around that set of SKUs. So what I really want to be is I really want to be at one single SKU per generation and a single form factor in each generation. And so when I go out and I build my Benes fabric and I have a fabric like this, what I do is I make each pod a separate generation. So each of these pods down here is a separate generation. So everything in this pod would be a single type of SKU of box and optical stuff and fiber cables and everything else, and everything here would be the same, and everything here would be the same. So this allows me to reduce the amount of work that I'm doing in my data center to keep everything running. So that's what's going on the physical end. So now let's look at the changes that are going on in the data center from a control plane perspective, because everything physical is going on at the same time. There's a complete earthquake going on in the control plane side of my cloth fabrics or of my Benes fabrics or whatever they happen to be. If I look at my current way of doing things, or my current and past, Facebook runs BGP. BGP is an internet routing protocol that's used to string the internet together. Hopefully I don't lose the audience too much here talking about routing protocols and which ones are being used. But Facebook uses BGP, which is really designed to connect autonomous systems, networks together, to string the internet together. It's not really designed for data centers, but it's being used quite commonly in data center fabrics today. So Facebook, Microsoft, LinkedIn, and Google, all four started out or are currently using BGP at various stages. Why would you do this? This is primarily, so here is something that comes off of a Juniper network document. Here's another one that comes off of RFC 7938. You can find these kinds of charts all over the place. I'm not picking on Juniper or RFC 7938 specifically, but this is the kind of thinking that went through in most of the big scalers or most of the hyperscalers when they chose to use BGP. So things like prefix distribution is the same. BGP allows you to do a lot of policy around traffic tagging, traffic engineering, prefix filtering, and things like this. There's also a huge claim that BGP, because it runs the internet, actually does scales a lot better than other routing protocols might. So here you can see the requirements from 7938, which is an IETF document. So there's a topology that can be scaled horizontally. This is solved by using a spine and leaf. And define a narrow set of software features supported by a lot of networking vendors. You'll note that this Rec 2 actually falls into this multi-vendor stability situation right here. Simple implementation in terms of programming and operational support. Again, this might fall into the BGP camp over here. Minimize the failure domain of equipment or protocol issues. This would fall into prefix filtering, traffic engineering, traffic tagging, things like this. Allow for some traffic engineering, which would fall into these policy steps, again, as always. So what is going on in the world right now is you're seeing Facebook. They did a paper on something called OpenR, which, by the way, they should have an RFC draft out for at some point, according to the people I know at Facebook. They are also using BGP, but they are using OpenR in parallel with it. Microsoft seems to be sticking with BGP for right now, although there are movements towards other things. LinkedIn seems to be moving towards something called Open Fabric, maybe plus BGP. Google, a while back, went to something called FirePath and is now moving on past FirePath a bit, but that's what they moved to. So everybody's kind of moving, the hyperscalers, not everybody, but the hyperscalers seem to be moving away from BGP right now. So why is this? What has changed? The first thing is our perception of policy is changing. This is primarily a result of of these things around SDN. So everybody is looking at this SDN model and saying, it's really kind of neat to have this overlay controller that can manage some parts of my network in a way that makes sense for me. So SDN is kind of changing the perception of policy. The other thing is I'm starting to see a lot more complexity around mixing policy and reachability. So what I need to do is I need to rethink my policy and understand my policy better. Another movement that's going on is my perception of configuration is changing. Most networks on the enterprise side and even in data center networks are moving towards a single source of truth. This is handled through DevOps, which you've probably heard of before, someplace in your travels in network engineering or in the world of just reading IT stuff. So DevOps is really pushing this concept of single source of truth versus minimal or no configuration. So they're trying to take configurations that exist and not minimize them, but to automate those configurations. What is happening is a move towards this concept of minimal or no configuration, what might be called autonomic, or even going beyond zero-touch provisioning. So DevOps tries to move to a concept of zero-touch provisioning. But in reality, people are trying to move beyond zero-touch provisioning to just autonomic. I plug it in, I turn it on, and it just works. I don't even need to contact the server to get the right configuration. So there are a couple of things that I need to do if I'm going to look at this kind of a world. If I'm going to have this controller sitting up here that's actually managing this network, the controller needs to have a full view of every link and every device in the network. The controller needs to understand where the network is and what the network is doing. The easiest way to do this is if you have a link state database. If you have a link state view of the network. Now, link state is completely different than the way BGP operates. BGP is what's called a path vector protocol. A link state protocol actually operates in a completely different way. So for this particular solution, or when you start thinking about pushing a controller that's going to push my policy into the network, all of a sudden the view of the network that is given to me by a link state protocol is better than what BGP gives me. So what I want to do is I want to actually pull all of my policy out of the routing protocol and shove it into this controller, which simplifies the routing protocol as well. So now what happens when I look at this, I can say, well, I have prefix redistribution. This is my BGP view of things, right? This gives me this traffic engineering type stuff and prefix filtering type stuff that gives me a lot more information that I can shove into the routing protocol. What I'm seeing now is I'm seeing prefix filtering, traffic engineering, and traffic tagging. All of this policy stuff is being handled by the overlay and by the controller. So I've removed those out of my requirements. Now what happens is also I see my multi-vendor stability is important, but I'm actually kind of backing off on that because I'm disaggregating. I'm buying my control plane from one company and buying my NOS and my hardware from a different company. This means I actually have a bit more control over the stability of my control plane and how this works. So what I've done by doing this is I have put a controller on top which takes care of my policy. I'm disaggregating, which takes this stuff out. But now I add more stuff in here that is a requirement. I've added 2 new requirements. One is auto configuration, one is full view of topology. So now auto configuration I get automatically with OSPF and ISIS. You can do this with BGP, but it has to be modified and messed with. And again, full view of topology is the same way. So what I'm seeing is I'm seeing this movement towards moving towards auto computing things and moving away from the configuration and DevOps world. So again, BGP gives me my policy, but mixing topology, and reachability is getting very complex. It's well known and it's widely implemented, but this is valid if I'm relying on vendor-driven software in a mixed vendor environment. But disaggregation changes the game. So BGP scales better, but BGP, the scaling problem in BGP can be solved. So again, if I think about BGP as my control plane, it can handle more prefixes, great. But I have mitigating factors against this. I'm running much faster processors. I am optimized my routing protocols. I've changed the way that I'm managing my network, so most changes don't really impact things. So what I'm finding today is I'm finding that link state protocols can actually carry the number of prefixes required in a data center fabric quite efficiently. So BGP can handle more routers in a single network, but now what I can do is I can actually modify ISIS to take that flooding advantage away and make it where ISIS can run in these link state fabrics. So what I'm actually seeing here is a bunch of different things going on at this point. Things like Open Fabric. I don't know if let me look real fast and see. I have movements like Open Fabric, like OpenR, all of those things I had way up in this slide. If I look way back here, these things are link state based, and they are challenging the dominance of BGP as the go-to protocol for these data center fabrics. So we're seeing a total shift not only in the underlay, in the amount of, or not only in the physical hardware and the way I'm building things, but I'm starting to see a shift in the way I build the control planes in these networks as well. There are a lot of different choices and different things. I'm not going to get too technical in this presentation, so I'll just kind of pass through those slides, and if you want to look those up. So I actually have a question here. Hyperscalers, I understand, but do you think we're going to go post-BGP in the next tier down? So the next tier down, I think you mean by next tier down, larger scale or even smaller scale companies. So here's the thing. I think that as we move towards more hybrid, so let's begin with where BGP came from in the larger enterprise networks. And I use the term enterprise guardedly because I don't like that term. But in the larger enterprise networks. So if I look at my Adobes and I look at my Disneys and I look at my Bloombergs and I look at my Bank of Americas and people like this, they are now using spine and leaf fabrics with BGP as their data center control plane. Why? Because this is where the hyperscalers went first. So first of all, I think you will see a trickle down from the hyperscalers as they get these things running. For instance, Open Fabric is what LinkedIn is looking at right now. And Open Fabric was just pushed into FR routing. So you can actually go get that as open source code and play with it. At least parts of it are. The ISIS parts of it are, not the controller part. But nonetheless, there are parts of the code that are out there. So now you can actually go get this stuff. So there will be a trickle-down effect to start with. The second thing that we can think about is that as we want to move more towards hands-off networking, where the network just takes care of itself, I think we're going to be pushed more towards getting away from BGP as the go-to protocol. Now, I know the folks at Cumulus disagree with me on this. I know there are other folks that disagree with me on this, and that's fine. I just tend to see this as I'm seeing people do it. I see a lot of interest from other companies that you might consider smaller than a hyperscaler, companies that are pushing 150, 120,000 blades in their data centers are looking at other solutions now and starting to think, well, why am I running BGP? So now let's talk a little bit about future directions. First of all, there is this concept called intent-based networking. So intent-based networking essentially abstracts out your control plane, or not your control plane. Sorry, I always say this wrong. Intent-based networking abstracts out the configuration management and moves beyond DevOps. So in DevOps, I have a single source of truth, and I push things into this single source of truth. And then there are a set of modules that talk to each kind of box underneath that single source of truth. So I take the single source of truth, I marshal it into a particular language, maybe it's Yang, maybe it's JSON, maybe whatever it is, and I do this, I take these things and I push my single source of truth down to modules that allow me to talk to a GNOS box, or talk to a Cisco box, or talk to an Arista box, or talk to a Cumulus box, or whatever the case might be. And then these are pushed down onto the physical boxes. Where intent-based networking is interesting is that rather than pushing a set of configurations or ideas down here, I'm actually pushing my intent down to my single source of truth. So I add a translation layer in here that translates what I might consider my intent into something that allows me to make that into a set of possible, into a model, a unified model that goes into my single source of truth, and then those are translated. Now what's interesting is then I pull off of these devices, I pull back through a translator, and I look at the current configuration of the entire network against what I intended. And that gives me a feedback loop back. So where this goes is it goes into, ultimately, potentially things like self-healing, which is an overused term, but it does have some kinds of meanings. So who are people working in this space? Well, Avi Networks and Anuta and Apstra and Forward Networks, and Cisco actually has some work going on in this area as well. So intent is really, really interesting, and it's an interesting thing that's going on right now. Another interesting thing that's going on right now that a lot of people are talking about, but they don't necessarily understand the background of why this is happening, is fog or edge computing, right? I'm moving things back to the edge. So let's begin with a bit of internet history to understand why this might be happening. So back in the old days, I had content providers, and these content providers paid transit providers who then connected to edge providers, and these edge providers connected to the end users. So these guys out here are called eyeball networks because they connect to the eyeballs, the actual people looking at their computers or their cell phones or whatever the case might be. So this is a really cool way of doing things. The transit provider gets paid by the content provider and the edge provider and everybody else, and they provide long-haul links and all the logistics that go with specializing in building these large-scale transit networks. And then your content providers focus on building content, and your edge providers focus on connecting to these eyeballs. Well, what has happened is that the content providers are actually now connecting directly to edge providers and to internet exchange points that in turn connect to local edge providers. So you can see immediately what's going to happen here is this paid link is going to reduce in importance and in the amount of money these transit providers are making. So what this means in reshaping the internet is I'm actually moving from a world where I'm doing a more of a, let's see if I can draw this for you because I thought I had it in the slides and I don't, where I'm moving from what I might call a scale-free network where everybody connects to the transit providers and the transit providers are connected to each other with big links. So everybody connects to the transit providers, to a world that is more hub and spoke. So now what I have at the top is I have my content providers, and they all connect directly to the edge connections. So everybody at this content layer actually connects directly to these edge connections. So this is interesting because it means that today, if you're sitting down here and you go get content, you're normally going up through the edge provider, through a transit provider, to the content provider. Well, that's not happening anymore. I'm actually going directly from here to my edge provider up to my content provider directly. Well, now what the content provider is deciding, well, why would I do that? The reason I would do that is because my entire point as a content provider is to get content to you as quickly as I possibly can. So what I'm doing is I'm trying to move my content closer to my eyeballs by short-circuiting and cutting the transit provider out of the loop. Well, what can I do to make this even faster? What I can do is I can take the content that's sitting up here and I can move it down to the edge so that I'm actually as close as possible to my user. So now when I start thinking about this, all of a sudden lots of use cases come up that I can do this with. So this is what a CDN essentially does, a content distribution network. But I can actually increase this by literally doing my computing at the edge rather than just caching content. I can actually literally do my computing at the edge. So this is where I get into what's called edge computing, or fog or something, whatever you want to call it. So edge computing. So what I'm actually doing here is I'm stretching my fabric across the edge provider's network or into my edge provider's network. This is really useful for a large range of things that are going on. So this is why you're actually seeing this come out as a big thing, this concept of edge computing, is that I can actually stretch my network and push content, not just content, but actually stretch it and push compute to the edge. So that is it for my slideshow. If anybody has questions, of course, you can push them here, or you can always reach me at various places. The easiest place to get in touch with me is just to reach out to me on LinkedIn. So I guess that's it. I don't know if Brightspace wants to step in now and say anything, or if there is some sort of I'm assuming there's some sort of a review of this where you can rate the session. You should fill that out if you can, and do that work as well. And again, feel free to reach out to me on LinkedIn or other places. You can find me at rule11.tech. You can find me at the Network Collective. You can find me on LinkedIn. You can find me through email. My email address is pretty easy to find, either on LinkedIn or other places. So that is it for today. Thanks for coming to the webinar, and let me know again if you have any questions or anything like that. And if there's a survey after this, please remember to fill that out and let us know what you thought of the webinar and the content. Thanks.